In 1949, a Department of Defense study group selected Cape Canaveral as America's first long-range missile test facility. The Cape was primarily undeveloped land when the Air Force began building. Here, missiles launched eastward could take advantage of the Earth's 1,100 miles an hour easterly rotation. The area was acquired at minimal cost, and there were important range safety features. Facilities could cover more than 20 miles of coastline, minimizing damage in the event of mishaps. There would be no flights over populated areas, and two broad rivers between Cape and mainland formed a natural maximum safety zone. The flat terrain meant no obstacles for instrumentation systems, and Weather Bureau records showed excellent weather conditions, 360 flying days a year, plus the fact that the eye of a hurricane had never passed over the Cape. All these factors added up to an excellent range potential. The Air Force Eastern Space and Missile Center was born with a slab of concrete, painter's scaffolding, sandbags, the latest radar equipment available, and a few cinetheodolites and cameras. In July 1950, the first launch test involved a captured German V-2 modified with a WAC Corporal second stage named Bumper. It was the first in a string of successes, punctuated by occasional failures as research and development testing progressed. The Lark was one of the earliest. Matador, forerunner of a series of cruise missiles. Snark, Mace, Beaumont, Navajo, Redstone, Thor, Atlas, Titan, Minuteman, and the Navy's Polaris, Poseidon, and Trident. The ETR also supported NASA programs with Air Force-developed boosters. Atlas Centaur, Thor Delta, and Titan Centaur. In growing to test each improved vehicle, large and small, the range acquired the ability to reach into deep space. Over the past 30 years of R&D testing, many changes evolved. At one time, Grand Bahama Island was the most distant downrange station, 150 miles from the launch site. But soon, others were needed. Currently, Grand Bahama, Antigua, and Ascension Island are major island tracking installations which comprise the range. Since its inception, the assigned mission of the range has remained constant: to provide facilities and support services to launch and test missiles for the Department of Defense, NASA, and friendly foreign governments. Our main launch activity occurs at Cape Canaveral Air Force Station. Cape resources include many launch facilities, both large and small. Sites no longer in use can be reactivated, and there's room for totally new installations, such as a multi-million-dollar complex at the tip of the Cape, housing checkout, testing, and operations of the Trident II missile systems. In the industrial area, hangar and office space is available, with buildings for storage, assembly, and testing of items of all sizes and descriptions. There are facilities for indoor testing of sensitive components and storage areas for hazardous propellants and other chemicals, as well as fully staffed facilities to help solve technical problems. Long-range weather forecasts are continuously updated along with day-to-day forecasts. Range communications media include high-capacity submarine cables to and from Antigua Island and an assigned spectrum of radio frequencies, including satellite relay capabilities and customary hardwire modes. With its own flight control tower, the skid strip handles the largest air cargo transports. Contractors supplying rocket components from entire stages to the most delicate satellites and test equipment often prefer direct flights to the Cape. This avoids potential hazards of prolonged land or sea travel. For an illustration, the Army uses the Cape for the operational testing of its Pershing missile systems. After being flown directly to the Cape from Europe, missiles and launch equipment move to the launch site. Crews then go on standby alert status until surprise firing orders are issued under simulated combat conditions. Ships of all sizes can dock at Port Canaveral at the south end of the Cape. Range instrumentation ships and Navy support vessels make this their home port. Fully equipped, they can collect telemetry, optical, and radar data from stations anywhere on the 7 seas. They afford a wider choice of test flight trajectories by filling gaps between land-based stations. The nearby submarine turn basin is another unique facility at Port Canaveral. Channel dredgings enable it to accommodate the nation's largest submarines. In fact, the long wharf can dock 2 vessels at a time, while the elevated mobile crane loads the largest Trident missiles on board. Locks at the west end of the port give shallow draft vessels access to the Banana River, and a barge canal cuts across Merritt Island to the intracoastal waterway. The key to successful R&D testing lies in prompt acquisition of accurate metric, telemetry, and electro-optical data. Program requirements dictate whether needed information can be obtained from a single source, 2, or all 3. The range collects all 3 primary types of data. Metric, using spatial measurement to determine flight path. Telemetry, with information measured on board a vehicle transmitted to a receiving site, and electro-optical observations recorded on film or videotape. There are 4 sources of metric data. Optics, giving azimuth and elevation angles. Target tracking pulse radars, which yield range in addition to angles. Navigation location systems, which give geographic position of ships at sea. And acoustic impact location systems for determining the geographic positions of bodies re-entering the atmosphere. The MILS, Missile Impact Location System Target Array, is an example of the latter. Sounds from a splashdown are picked up by a Pentagon array of underwater hydrophones. Mid- and long-range target arrays are established near our downrange stations at Antigua and Ascension. The FPS-16 radar near the skid strip can range out to 1,000 nautical miles under favorable conditions. 2 mobile C-band radar systems provide safety support by triangulating missile location during early flight. From this location, MCBRs have line of sight to the missile and track manually to a 15-degree elevation. Then the automatic skin or beacon tracking system takes over. The on-axis FPQ-14 radar at Patrick is known as the MIPR, Missile Precision Instrumentation Radar. The MIPR represents one of the largest radars on the center, with a tracking limit of 32,000 miles. By combining solid-state hardware with components tied to advanced computers, on-axis radars return precision data in near real time. Easily star calibrated, they provide highly accurate data. On-axis systems are available at Patrick Air Force Base, Grand Bahama, Antigua, Ascension, and on Merritt Island. All these radars send important real-time data to range safety. A range safety officer is on duty during every launch to ensure that no flight deviation can endanger either life or property. In addition to closed-circuit television and real-time verbal reports, he relies on 3 computer-generated electronic displays. One of these is the impact predictor. It has a map outline and shows the intended flight path flanked by safety limit lines. Moment by moment, it shows where debris will impact if it becomes necessary to end the flight. Other displays can be called up to show azimuth, elevation, and telemetry information. At liftoff, data from these radar systems is fed directly to the Cape. The cyber computer in the Central Computer Complex system combines these radar inputs and delivers them instantly to electronic displays, which are the prime input to the range safety officer's decision-making responsibility. Our 3 island tracking stations are the backbone of the Eastern Test Range and vital in performance of our mission. These stations are unique settlements in themselves. This is Grand Bahama Island Station, known as GBI. Each one is like a small city, virtually independent of the local economy. GBI, about 60 miles east of Palm Beach, Florida, also has a range safety command destruct capability. This is the island station closest to the Cape. The farthest island station is Ascension, a volcanic mountaintop rising in the middle of the South Atlantic. A British possession, Ascension is roughly 7 miles in diameter and lies about 5,100 miles from the Cape. A 10,000-foot landing strip is regularly used to airlift supplies and personnel. The alternate contact with the outside world is this minimum docking facility, limited to shallow draft vessels. The main base has all the features of a small city: housing, distilled water, electric power, and dispensary, among others. The barren, cinder-covered hills offer ideal locations for a variety of instrumentation to record the signals of vehicles re-entering the atmosphere. The TTR, or Target Tracking Radar, and the TAA-3 telemetry dish are typical of the instruments gathering data on Ascension. Several systems are involved in returning downrange data to the Cape. From as far as Antigua, clean data, free from interference or background noise, is sent back by underwater cable. Ascension, on the other hand, relies on satellite links and high-frequency radio. Original data recordings also returned by the quickest alternate means to provide a backup. Telemetry supplies information on the internal status and operation of test vehicles. Information such as engine or skin temperatures, fuel flow rates and cutoff times, stage separation, and many other events are vital in R&D evaluations. Onboard transmitters speed this information to ground receivers. The smallest receiving antenna, 7 feet in diameter, is also the largest airborne telemetry dish. It's mounted aboard the Advanced Range Instrumentation aircraft, ARIA, which may be called in on tests requiring their special capabilities. The largest receiver is the 85-foot on-axis computer-controlled parabolic antenna at Grand Bahama. The Advanced Range Instrumentation ship Redstone carries 4 30-foot telemetry antennas. In addition, each downrange station has one or more of these important systems. At Tel 4 on Merritt Island, there are 33-foot and 24-foot auto-tracking telemetry antennas. Antigua has a dual telemetry installation with a 33-foot and an 80-foot signal collector. These powerful receivers minimize onboard power requirements for signal transmissions. On certain small test projects, optics instrumentation is the only required resource, but the range is prepared to obtain optic data from tests of every magnitude. The largest mobile system is IGOR, also known as MITS, Mobile Instrumentation Tracking Telescope System. The lens has an 18-inch aperture with a variable focal length from 180 to 500 inches. Permanently mounted in elevated domed observatories are the ROTI, the acronym for Recording Optical Tracking Instrument. Its telescope has a 24-inch aperture and a 500-inch focal length. The 48-inch ITEC south of Patrick is a unique telescope system. Using on-axis drive, it can track a Cape launch or a satellite in orbit. A mobile optical tracking system, or MOTS, carrying up to 4 cameras, combines infrared and television remote control. It can be placed within a restricted zone close to the action, but without endangering the operator. The Swiss-built Contraves records a target image plus azimuth and elevation data. Generally, 3 or more are used for triangulation purposes. Shielded cameras provide close-up studies of detailed action. Timing is the key to correlating inputs from all these diverse data sources so that a complete history of each test emerges. Pulses originate from an atomic clock, corrected to microsecond accuracy with the U.S. Naval Observatory. During a test, the timing on all data is recorded simultaneously in increments down to 1,000th of a second. In this way, thousands of bits of radar, telemetry, and optical data are accurately matched within a single chronological story. Generally, raw digital or analog data is received on magnetic tape, on various types of film, and on other media such as punched paper tape and cards. All these are converted to computer format, then processed as required. The prime data reduction computers include the system in the technical lab at Patrick, plus the real-time computers at the Cape when they're not involved in launch-related demands. Center experts have created an advanced level of processing techniques to assure that maximum usable information is developed from the raw data inputs. The results are produced in any format and medium required by a range user. But the range isn't just an array of mechanical and electronic devices. It's made up of highly skilled people who make certain that these resources are used effectively. The blue-suiters, civil servants, and contractor employees have set a record which speaks for itself. Industry and civilian neighbors welcome and support the range operation admirably. The Air Force has built a superb test range and proven its capability to support tests of the largest as well as the smallest of devices. Even tracking a small tactical surface-to-surface missile like this one, the Penguin, wasn't beyond the capability of the range. In spite of Penguin's small size, short range, and low trajectory, the range still supplied 100% successful support. Any portion of these advanced resources is at the command of potential users who require a test site. Because this complex facility is in full operation, important cost savings are available. Experienced personnel have developed efficient procedures for conducting thousands of tests of all types and are ready to provide the services users may require. Not content to remain with the status quo, the range is constantly striving to upgrade and improve its already proven technology to meet new challenges of the increasingly complex missile systems being tested on the range. At Patrick Air Force Base, headquarters for the range, Eastern Space and Missile Center personnel are hard at work planning for new instrumentation systems and facilities. These will not only enhance our support posture, but will enable us to perform our mission in a more cost-effective manner. A few of the other improvement and modernization projects, either in planning or implementation phases, include a new state-of-the-art instrumentation facility being added about 95 miles south of Patrick at Jonathan Dickinson State Park. Equipment from the range's deactivated Caribbean tracking station at Grand Turk will be used, including a radar antenna, 4 telemetry units, command and flight test support systems, and a microwave relay to the Cape. The new facility will become operational in 1987. It'll be essential in support of the Navy's Trident II missile systems, among others. The improvement and modernization program also includes updating the existing telemetry at 4 sites, as well as changing over to SATCOM to meet the growing needs of future users. Phased array radar now being planned for the Cape will enhance our ability to track multiple trajectories, covering more targets more accurately, both at greater speeds and greater ranges. Other work includes consolidating the Range Control Center, the Central Computer Complex, and the Communications Facility into a Test Operations Control Center. State-of-the-art planning along this line would take us well into the next century. Furthermore, improvements like this would add to our capability in supporting future space programs of the highest national significance, such as the small ICBM and perhaps the Strategic Defense Initiative. Full utilization of the Eastern Test Range benefits both its present as well as prospective clients and assures the United States of maximum returns at minimum cost from its investment. That's important to us and to you.